In the last couple of videos I've been showing how I've attempted to read the contents of the ROM board from this HP9830A desktop calculator. I suspect there is a fault in one or more of the ROMs, and I wanted to firstly confirm that, but also see if I could read the data from the rest of the ROMs and at least give myself a head start on trying to extract the code from the patent. My plan is to produce a replacement ROM board, but obviously I need the code to put into it. Now, somebody mentioned that, could this be a speed issue? As I'm sure you probably know, that as ICs age, their performance tends to degrade. They quite often don't just fail. You'll find that outputs start to drop, they start to slow down in their response, and in fact probably 10 or 15 of the ICs that I've replaced in this machine were actually shown as working on my IC tester, but when you put a scope on them in the machine, the signal levels just weren't quite high enough to drive the follow-on circuits, and that's something that you need to take into account with old machines. So it could be the case that the ROMs have just degraded to the point where they're not quite fast enough and they are being pushed at a quite high rate. This machine does have an 8 MHz clock, which is quite fast for the time. However, I had taken that into account, and I just thought I'd give a quick update in this video to show the steps I took to make sure that wasn't an issue. And in fact it did prove to be the case that speed is partly the issue here, but not entirely, and I'll explain what I mean as I go along. So the first thing to bear in mind is that the clock rate that you can drive the ROM board is obviously governed by the machine, the HP, and in the programmer here it is running about the same speed with regard to the address lines and the reading of the ROM itself. There are a couple of things I thought I'd just mention before I proceed, because they were mentioned as well. Firstly, when you try to read a ROM in an EEPROM reader like this, it will try to read the manufacturer's code from the EEPROM, and the way it gains access to the internal manufacturer's code within the EEPROM is to drive address line 9 in this case to 12 volts, and so you need to be careful if you're doing what I'm doing here and hooking a non-ROM circuit, because if you just put A9 direct to a TTL IC, then obviously when the programmer drives that line to 12 volts it will destroy the chip. So although you probably can't see it here, there is a resistor and a Zener diode on that line. It's just A9. The particular line varies from IC to IC, but just be aware of that if you are using a programmer for this purpose. Also, one thing I haven't shown, this is the schematic for this. It's simplified just so it was easy for me to work with. What I haven't shown is that there are pull-up resistors on all of the data lines, because the output of the board is normally connected to the T register, and the pull-up resistors required are actually on the T register board, not on the ROM board. So I have actually fitted them on the edge connector. Again, you can't see them, but just bear in mind they're not shown on the schematic, even though they are actually there. But the main point of this video with regard to the speed is that if we do a quick run to read this board, then on the scope I will do a single shot capture of the data being read. So if I just do that now, I don't know how well this will come out on camera. This scope's not very good for this sort of thing, it's not very bright. But I've got the scope set to 10 microseconds per division, and as you can see it is running one address line 0 every 10 microseconds, and I'm using that as the input to the logic analyzer. So in other words, it's allowing about 5 microseconds for the data to settle from the memory card, the ROM card. Now that would normally be fine for the chip itself, but because they're configured in a way where the outputs on many of them are connected together, then that does tend to slow them down a bit, and as I said earlier, as they've aged, then their performance will have degraded still further. What I've done to try to determine if there's a speed issue is, although I've got address lines going into the card and it requires address A0 up through A12, I'm not connected to A0 up through A12 on the actual programmer socket. So I'm actually connected from address line 2 up through 14. So what I've done is just shifted all the address lines up 2 places on the programmer socket, and the effect of that is to essentially divide the read rate by a factor of 4. I'll just demonstrate that on the logic analyzer to further clarify it. So I'll just move the camera. Okay, so on the analyzer I've just got the first 3 address lines connected. I've got them configured or identified here as A0, A1 and A2, and then a clock. Now A0, A1 and A2 are not connected to A0, A1 and A2 on the programmer socket. They're actually connected to A2, A3 and A4. So while we had a 10 microsecond cycle time shown on the scope was connected to A0 on the programmer, and that's what I have the clock set to. And again, I have the analyzer in state mode with the input clock fed from A0 on the programmer socket. Notice I got quite a big offset set here, and that's simply because the first 100 or so cycles of the programmer are it attempting to read the manufacturer's data, etc., from the ROM, which we're not interested in. So if I now trigger the analyzer, I've got it set to trigger on the rising edge of A0. So what we have now is the bottom trace is the clock input, and that is actually A0 on the programmer. A0 on the analyzer screen is actually A2 coming out of the programmer, but because the programmer does not deassert the address lines, it just essentially counts them up as it reads the ROM. Then what I've effectively done is divided the clock by 4, and that's what I'm using to control the board. However, it also means that because the programmer is still reading data on each of its address 0 lines, I'm actually reading each value coming from the board 4 times. And that was intentional. I wanted to do that because if it's a speed issue, then obviously what we should see is the value settling through each of the subsequent reads. And so we'll now go and look at the software and see if that's what I found. Okay, so we're looking back at the software that I demonstrated in the previous video. As you can see, I've modified it quite a bit, and I'll explain what the modifications are for as we go through. But essentially the way it works is we select the file that we've generated from the EEPROM reader. It's just a binary file. We give the file an output name, and then we decide what format we want the data in. And we can also now limit the number of instructions that the file will contain. And also we can decide or tell the software how many duplicates there are in the data. And of course there are 4 in this case. So I'll limit the file to 100 instructions. We'll process the file. If we now look at the data that's being produced, then we'll see there are duplicates. There are essentially blocks of 4 instructions, and if the card is responding quickly enough, they should all be the same. So the first instruction is taken after 10 microseconds. If you recall, that was the basic cycle time for the EEPROM reader, and then 20 microseconds, 30, and the last one's at 40 microseconds. And in theory they should all be the same if the card is responding quickly enough. So if we go back to the software, I can also specify a start address, so we'll read the entire contents of the first pair of EEPROMs. If you recall, they're in pairs, the 512 byte EEPROMs, and the pair gives us a 16-bit word output. So if I run this now, notice that it's saying here we're getting no errors. Now the error count is not errors against the original patent information. It's just saying that all 4 copies are the same for each of the records that we've processed. So in other words, all the data that we've produced from the first 2 ROMs on the card are intact, and in fact they do match what's in the patent. However, if we go back now to the software and I change the end address so that it's higher, I'll put in 760. If I now process the file again, notice we've got some errors. And if we now look back at the file, scroll to the end, you can see again we've got blocks of 4 instructions, but in this case you can see that this first one is incorrect. The last 5 digits are correct for all 4 copies, but in the first one of the bits has failed to respond in time, but it has responded after 20 microseconds. Now also that means this card or this ROM is way too slow to work in the calculator, which has a much shorter cycle time than this, and that would cause problems. However, even if we go back to the software and we can turn the duplicates off, reprocess the file, it's still showing errors, but it's actually outputting the non-error values. In other words, it's outputting all the 40 microsecond values. And if we go back to the file, then you can see there are no longer duplicates, it's just showing the last readings that it took. But unfortunately these also don't match, or they don't all match what's in the patent. So either the patent information is incorrect, which could be the case, or the ROMs are indeed failing, or a combination of the two. What I'm going to try is putting the card back into the calculator and changing the crystal in the calculator for maybe a 1 megahertz crystal, just to slow it down, and see if that changes the results that we're seeing from the calculator itself. I still suspect the ROMs are damaged, and what I'm going to have to do is create a new ROM card. But this is a fairly good way of testing, and it was quite interesting, so I thought I'd do an extra video just to show it. If you've got any questions or comments or advice, then please leave a comment.